Here's integrated 3. It's problem 5-70. It says make a table and complete graph for the function f of x equals x minus 2 over x plus 2. Well, let's start there. We have to make a table and a complete graph. So a table, I made a little t table with the x and the y, and I just plugged some negative numbers. Usually I just do -1, 0, and 1, but that didn't give me a nice picture of the graph, so I did a lot of negative numbers, and I'm generating these numbers by plugging numbers in for x and then calculating y. So like if I put -4 in, that's -4 minus 2 is -6, and -4 down here plus 2 gives me -2, so I get a 3. So when I plug in -4, I get 3. When I plug in 3, I get 5. When I plug in -2, it's undefined, so that's going to give me an asymptote at 2. And then I kept going down the list, plugging in some numbers. I noticed that I was getting these fractions. And actually, I'll show you, just these ones that are done in pen, these are the ones I started with. Oh, wait, this isn't the graph that I want to show you. Here's the graph I want to show you. I got some points, but it wasn't really obvious where the graph was going, and it's telling me to make a complete graph. So I do have a y intercept right here at 0, -1, and I have an x-intercept right here at 2, 0. I wasn't really sure. I know this asymptote, the reason I have this asymptote graph right here is because when I plugged in -2 for x, I get undefined. And so we talked a little bit about graphs with asymptotes. I plugged in some extra points like -5 and -6 just to see what I would get. I actually plugged in -7. I plugged in a lot of points, and I convinced myself that this graph will never equal 1. It'll never equal 1 right here. Like if you start, and I would encourage you to plug in some really big numbers. Oh, you can't see my hand. Really big numbers here, and see if you can get your function to equal 1. It won't equal, y will never equal 1, and then it kind of made sense, because if I plug in x, I'm plugging it in on the top and the bottom, and for a fraction to equal 1, it has to be the same thing on the top and the bottom, but it'll never be the same thing because we've got a -2 up here and a 2 here. So I know that sounds a little crazy. If you plug in some numbers, it'll make more sense, but there's this horizontal asymptote because the y value can never equal 1. So that asymptote helps me. I don't have to plug in any more points now because I know that the graph's going to follow the asymptotes. So this one that I have all graphed already, that is the graph of the original function, and this is the table of the original function. So that was the first thing they told us to do. The next thing they told us to do was, letter A, make a table for the inverse and add the inverse to the graph. So I'm thinking they wanted me to add it to the graph of the original function. And state any restrictions for the function and its inverse. Well, the function, the restrictions that I found when I graphed it was that there's an asymptote at x equals -2, a vertical asymptote, and there's also a horizontal asymptote at y equals 1 on my original graph. So those are the restrictions that are on the original graph. Now, I suspect that those restrictions on the original graph are going to apply to the inverse. So the table of the inverse is simply, I don't even have the equation for the inverse yet. Don't look at it. We'll show you it later. I just flip-flopped the x's and the y's. Like if the original function was -4, 3, Then for the inverse, it's 3 comma negative 4. See how that goes? Negative 3 comma 5 is 5 comma negative 3. So I went and I just made my table just by swapping the x and y values. And I actually took these and I made these little circles. Those are the points that I plotted. And then I realized that this could take up a lot of my time, and I want to kind of use some things that I know about the original graph to help me do a better job with the inverse. So I do know that an inverse, like when we have an inverse graph, the x and y values change places. So that tells me something a little bit about these asymptotes. Since the original graph, the x values can never equal negative 2, I think the y values on the inverse will never equal negative 2. So I'm going to draw a little asymptote right here. And since on the original graph, the y values can never equal 1, that means the x values can never equal 1 on the inverse graph. It's like the domain and the range, they just get swapped. And so now that I have these dotted lines and see these little circles that I made, those are the ordered pairs that I plotted. Now I can kind of tell what they're going to do. They're going to go like this. They're going to follow those asymptotes. So I don't have to bother plotting or trying to like plug in points. Like I know where it's going to go now. And this one's going to go this way. And it's a complete graph because I have the inverse graph is this dark blue one, and I have my y-intercept, and I have an x-intercept. So there's my complete graph. My table came from just flip-flopping the table from the original, and the original table came from plugging numbers into the original function. But they also, letter B wants me to write the equation for the inverse function. And this, I don't know if you guys know the algebra on how to do this. So I'm going to kind of walk you through the algebra for this. You can't do it just by, you can't just say, oh, I'm going to add 2 here and minus 2 here and multiply them together. It seems like you could, but there's an order that matters. So what I would do is just, the first thing is just to let the x and y values trade places. So see, I turned the y into an x and I turned the x's into y's. And then I'm going to solve it for y. And I'm going to do some little algebra tricks that I think you'll be able to understand. So I multiplied both sides by y plus 2 to get rid of that denominator. So these canceled out, and that's what's happening here. And then, so I have x times y plus 2. I'm going to distribute my x because I want to get all the y terms on the same side of the equal sign. And so you'll see once I distribute it, I have a y term here and a y term here. I decided to bring all my y terms to the right-hand side of the equation. So I added 2 to both sides. I know, I kind of skipped some steps. I added 2 to both sides, and I subtracted xy from both sides. Okay, so I kind of let them switch places a little bit. So now over here, here's my y terms, because remember I'm trying to solve it for y. And all I have to do now is factor out a y. Factor out a y, so that gives, because see, look, if I go like this times this equals this, this times this equals this. So I factored out y. And then I'm going to divide both sides by 1 minus x. And then I have the equation of my, that's the equation of my inverse. That's f inverse x. So I left it as 2x plus 2 over 1 minus x. And I was talking to one team, and they said it didn't look like the graph on Desmos, but I typed it into Desmos, and it does look like the graph. So we know that this blue graph, this is the inverse graph, because see how I flip-flopped the x's and the y's? But this is my solution that I just got algebraically. And see how it's the same exact graph? The purple graph is the same thing as the blue graph. And you can also, let me switch back. I'm making this thing a little too long, so I'll hurry up. If you want to do a little bit of algebra to this, you can multiply the bottom and the top of the fraction by -1, and then that allows you to write it this way if you want to. And this is f inverse of x. This is the inverse equation right here, f inverse x. And that was problem 2-70.